Talk about mathematical induction. So what is induction and why do we care about it? So induction is a type of proof. So it's a type of proof. So in math, we like proving stuff. We like knowing, okay, is this actually true what we are saying, or are we just taking the word for it? And induction is a proof writing method. So on one side, I'm gonna make like a division. So on one side, I'm gonna show you how to do it. And on the other side, I'm going to explain in simple terms what's actually happening. I'm going to give an analogy of a ladder, okay? So I'm going to draw a ladder here. So it's not going to be very artistic. So imagine this is a ladder, okay? A slanted ladder. Okay? So I'm just going to draw two lines. I'm going to draw the rungs in the ladder later. So how do you do induction? So number one, you state the base case. State base case. And we'll like go over an example of induction soon. But first, I'm just going to tell you how to do it. So state base case. So that transfers to us saying that, okay, the ladder has a first step. So we can get on the ladder, okay? So this is what the base case is. So 2, assume that the statement is true. So assume true for n equals k. So what this is saying is that assume that there exists some random step on this ladder. So let's assume that exists, okay? So this we're assuming. So we're assuming that we can get on that step somehow. Now this is the inductive step. It's called the inductive step. And what it really is the most important. This is the whole point of induction. As you can see, it literally says inductive step. And what this says is show true for show true for n equals k plus 1. So in our analogy, what that really means is, okay, if you're assuming that this exists, then we're also saying that, okay, if this exists, then we're going to show that the next step also exists. So we're going to show, so we've assumed this one is true, and we're going to show that, okay, if this is true, then it must be true that the next step also exists. And then we state our conclusion. So our conclusion states that, okay, since the next step is true, then it's true for everything. So we have an infinite amount of steps in this ladder. So I'll go over this analogy again if it didn't make sense. Okay, so we have a ladder, right? We're trying to go up the ladder. So I'm just going to draw a better ladder because this is not a good ladder at all. Let me draw a good ladder. Let me rub all this out. Okay, so we have all that gone, okay? So I'm just going to draw 2 straight lines. So I have that line, and I have that right there. Okay, so we want to go up this ladder. So we're saying state the base case. So base case means, okay, the first step exists. So this is true. We know that's true. Second one is saying assume true for n equals k. So this means that we're going to assume that some random step, let's say over here, we're assuming that this step exists, okay? And we're on this step already. So now I'm standing here. We started here, and then I moved to this step right here. Now what I'm going to do is I'm going to show that the next step in the ladder is going to exist. So this is going to exist. And think about it, right? If the next step exists, then it doesn't matter where I start. I can start over here. I've shown that it exists for any random step. So that means this step will exist. And then that's where you come to a conclusion. Okay, if the next step exists, that means that any step that we want, we can always get the next step from it. So I can have another step right here. And this is basically induction. It's saying that, okay, you're going to start somewhere. You're going to show that you can get on some random step, but you're also going to show that the step after that one is also going to exist. And then from there, you can just get on any step you want, and the next one will always exist because you already showed it by this point right here. This is the important step right here, the inductive step. And there's many cases of induction. So we can do induction on many types of proof, right? So today we're going to look at divisibility. Divisibility. We can do it for derivatives. I'm actually going to make 4 separate videos. We're going to do divisibility today, then we have derivatives, then we have summation, and we have sequences actually. I don't think I have a video on sequences, but I'm going to make the video on others. And we also have one on matrices. Matrices are very interesting when it comes to induction. So let's do our example on divisibility, and this will actually start making sense right now, because what does this ladder talk about, right? Okay. So, prove by mathematical induction that for all positive integers n, so we have to underline this, 5 to the 3n plus 32 to the n minus 33 is divisible by 31. Okay, this is very interesting. So remember, what was the first step? Base case, right? So base case means the proof, the very first thing. So and that's why I underlined this, because for all positive integers n, that means n is equal to 1 is our base case, because that's the first positive integer. So we're going to show that it's true. We're going to show that it's true for n equals 1. So when n is equal to 1, we have 5 to the power 3 times 1 plus 32 to the power 1 minus 33, which is equal to 125 plus 32 minus 3 is equal to 124. And this is actually equal to 31 times 4, right? 124 is 31 times 4, so true. So we do so true for base case. Okay, so we're showing that it's true for the very first step in the ladder. So if it's a ladder, we're showing, okay, we can get on top of the ladder now. Now we're going to show it's true for all positive integers n. But our second step was, remember, assume that it's true for some n equals k. You can make it any letter you want. You can make it f, t, whatever you want, so for n equals k. So we're going to assume that we can get on any random step that we want. So in this case, what we're saying is that 5 to the power 3k plus 32 to the power k minus 33 is divisible. So this is our assumption, is divisible by 31. Okay, so we have to assume that this is true. Okay, assuming that is true, what do we do now? Okay, so now we have to show that it is true, and this is the hardest part by far. So true for n equals k plus 1. Now how do I do this? Okay, so when n is equal to k plus 1, let's just put that inside here. Okay, so when n is equal to k plus 1, we have 5, 3, and then instead of n, we're going to do k plus 1. So we're going to have 3 k plus 1 plus 32 to the power k plus 1. Because remember, it's n here, we're going to put k plus 1 instead. So 32 to the power k plus 1 minus 33. Okay, we have that. Now let's expand the brackets here. So we have 5 to the power 3k plus 3 plus 32 to the power k plus 1 minus 33. Okay, so far so good. Now I want to write it like this. So we have 5 to the power 3k plus 3. So this is like 5 to the power a plus b, which is 5 to the power a times 5 to the power b. So that's the same as 5 to the power 3k times 125, because 5 to the power 3 is 125, plus, and again, this is 32 to the power k times 32, because 32 to the power 1 is 32, and then minus 33. Okay, so far so good. Now we have to think, okay, how do I go from here to proving, and how do I go from here knowing this is true by our assumption to proving that all of this is true? It might look impossible, but the thing about induction is it requires you to think just a little bit. And if you think about it, okay, let's notice something. We know 124 is divisible by 31. It helped us, right? In our base case, we go 124, and we realize, okay, 124 is divisible by 31. So what if I wanted to write this as 124 of 5 to the power 3k plus 5 to the power 3k. Okay, this is 125 5 to the power 3k in total, right? I'm just splitting it up. Plus, okay, and now I don't want 32 anymore. I want 31 32 to the power k plus 32 to the power k, right? So this thing right here belongs to this right here. This is literally all this is. And this thing right here, let me draw that better. This right here is all of this right here. So we haven't done anything. And then we have our minus 33. So we have minus 33. So still we haven't made that much progress, but something interesting is happening now. So this was just me using my brain a little bit. It's me thinking, okay, how do I like rearrange this in a better way that's going to be more convenient for me? Okay, so now we have this. So what can we do? Okay, let's bring 124 and 31 together. So we have 124 5 to the power 3k plus 31 32 to the power k plus 5 to the power 3k. So I've done this and this, I've put them together. Now I'm putting the 5 to the power 3k over here, plus, and I'm going to bring this 32 to the k over here, plus 32 to the power k, and then minus 33. Okay, so far so good. Now something interesting has definitely happened, because now look at this. We have 124 and we have 31 together. I can factorize this as 31 and then big brackets. Now 31 times 4 is 124, right? So I have 4 and then I have 5 to the power 3k inside here. Okay, I have that plus, and then just 32 to the power k. Because look, I have 31 times 32 to the power k. So this is 31 times 32 to the power k. And here I have 124 times 5 to the power 3k. So I have 31 times 4 is 124 times 5 to the power 3k. So I'm going to close those big brackets. And then over here, I just have the remaining 5 to the power 3k plus 32 to the power k minus 33. Okay, and now you should be seeing what's going to happen. Now look at this. This is just some number. All of this, whatever this is, I don't care what this is, right? Because the important thing is 31 here. This is some number x. Whatever you want to call it. You can call it whatever you want. So now we have 31 times x plus, and I'm going to put this in brackets. We have 5 to the power 3k plus 32 to the power k minus 33. Okay, so what's happened here? Okay, this is divisible by 31. Divisible by 31. Of course it is, because it's 31 times something, so of course it's divisible by 31. And this right here, what is this? What is all of this? Well, all of this, 5 to the power 3k plus 32 to the power k minus 33, is this right here. This is all that is. And what did we say? We assumed that it is divisible by 31. So according to our assumption, I'm going to draw that better because this is important. According to our assumption, this is all divisible by 31. So this is also divisible by 31. Well, what do we have now? We have, when n is equal to k plus 1, this whole statement here, so this 31x plus whatever this statement is, let's just call it y, 31x plus y, is divisible by 31. Because of course, if you're gonna have 31 times something, that's divisible by 31, and then you gotta add that to something that's already divisible by 31. That's like saying if I have 24 plus 36, okay, so I know 24 is divisible by 6, so that's fine. I know 36 is divisible by 6, so that's fine. And 24 plus 36 is obviously 60, and of course that is also divisible by 6, right? That's just how division works and addition works. So this whole statement right here is divisible by 31, but this is when n is equal to k plus 1. That means we have shown this thing right here. We have shown this next step over here. We have shown that this step exists. We assume that it exists. We assume that some step existed, and then we showed, okay, even if our assumption is correct, then the next step must exist. And now we just take the conclusion. And then usually the way you write the conclusion for these type of proofs is then by induction, the whole statement. So this whole thing, I'm not going to write the whole statement again, but 5 to the power 3n plus 32 to the power n minus 33 is divisible. So 5 to the power, I'll just write it again, 5 to the power 3n plus 32 to the power n minus 33 is divisible by 31. And that's it. That's the end. So usually when you finish a proof, you do this right here. That's the end of our proof. And what have we done? We started with the base case n equals 1 because it said for all positive integers n. So the smallest positive integer n is 1. So we started with 1. We showed that it's true. We got 124 and we saw 124 divides 31 perfectly. So it's true for the base case. We assume that it's true for some random n equals k. So k could be like 502, for example. We assume that it's true for that. And then we showed that when if it is true, then the next step, so it's going to be true for k equals 501. And we showed that by doing some manipulation right here. You should go and watch that again if it didn't make sense. But you just have to use your brain a little bit and think, okay, how can I rearrange this a phrase or like this equation that we have, not even equation, these terms that we have in a way that's going to be convenient for me to use for whatever I'm dealing with, which is in this case is dividing by 31. And when we did that, we saw that it's true for n equals k plus 1. And then we saw that that's divisible by 31. So then if it's true for n equals k plus 1, then it's true for any n that's positive, that's a positive integer in our case. So yeah, that's induction. I hope that made sense to you. If it didn't, just watch the video again, and if you have questions, write them in the comments. Please like, share, subscribe if you like the video, and yeah, let me know what else you want to see in future videos.